Chapter 1 of Stewart's Calculus Early Vectors is Vectors and Vector Functions. In this chapter, we have to talk about vector quantities in general, the algebra of vectors, and finally vector functions. Now, what exactly is vector quantity? This is the way our textbook author explained the vector quantity. The term vector is used by scientists to indicate a quantity that has both the magnitude and direction. Right here. The keyword, magnitude and direction. Vector quantities have both. For example, if you measure some mass of a certain object, 75 grams or something, does that kind of quantity has a direction? No, not really. It has size, the mass, but no direction. But for example, let's consider the position. You're traveling from here to some other place, 3 miles to the east and then 2 miles to the north, those kind of things. Definitely there is direction. Those kind of things are vector quantities. However, respectfully to our textbook author, I think there should be more. In my opinion, we have to consider 3 characteristics, not 2. Magnitude, of course, direction, but also we have to have a certain algebraic rules. Let me show you what those mean. This picture visualizes the magnitude. We have 2 different vectors, v1 and v2, blue and red, but they share the same magnitude, the same length, same size, and magnitudes are represented by absolute values, and they're the same, but they're 2 different vectors because they have 2 different directions. How about this? We have 2 different vectors with 2 different magnitude but same direction. So if you use this hat notation, that means the direction vector, and the directions are the same, but magnitude for blue is certainly bigger than magnitude for red. But that's not all. Vector quantities must have some algebraic rules. And this picture visualizes vector addition. Red vector plus blue vector, we simply use this parallelogram method to get the diagonal. That's how you get the sum of 2 vectors. Using this picture, you can clearly see v1 plus v2 and v2 plus v1 are the same. The addition is commutative. And you can prove all the other rules as well, but I don't think we're going to spend class time proving anything. So just remember this kind of visualization, parallelogram. And there's another vector operation. This is scalar multiplication, that is multiplying us by a certain real number. In this particular case, the real number that we are multiplying is about 0.24 something, a little bit less than a quarter, and consequently this purple vector is about a quarter size of this blue vector, a little bit less than that, because that's the number we just multiplied. This program, by the way, is randomized, so if you run it again, you're going to get different quantity. And k is now 0.16 something, so purple vector got even shorter because we just multiplied by even smaller real number. And in this case, k is nearly 1, a little bit bigger than 1, so purple vector is almost the same as blue, a little bit bigger. Oh yeah, I wanted to get something like this. K can be negative as well. That means the purple vector, W, points the opposite direction. This is negative 0.738 something. So in terms of size, it's a little bit less than 3/4 of this blue vector, but pointing toward the opposite direction. You can play with this. Run it over and over again if you're using Mathematica. If you're using CDF player, then of course you can read this, but you cannot really play with this. So that's scalar multiplication. This one changes size, and this one creates parallelogram. Interestingly though, the vector quantities do not depend upon the starting point. Here's a visualization. We have these 4 arrows, green, brown, blue, and red. They all represent the same vector actually, the different manifestations of same vector, because it doesn't matter where we start. All we need is magnitude, the size, the direction of the arrow, and whether they follow all those algebraic rules or not. Now, if you're free to choose the starting point because the starting points do not matter, what is the best starting point, the simplest starting point? In my opinion, that's the origin. You see, all these arrows represent the same vector because it doesn't matter where we start. I can choose any starting point. Why don't I take the simplest point in the entire plane, the origin, as a starting point? In that case, you're going to get this kind of rectangular coordinate plane, and a vector v, which is represented in blue, have one-to-one correspondence with the point x comma y. Those kind of things are called components of vectors. And in order to distinguish from points, we use those pointed, those triangular parentheses rather than the usual parentheses. Now, on print, we use these this triangular parentheses, but if I write with my marker, sometimes it's going to be very difficult to distinguish one and the other, especially when I write quickly. You just use your common sense. By the way, it'll turn out that they don't really matter too much, to tell the truth. Why? We're going to answer it in the next item here. One of the most important type of a vector, as a matter of fact, the most important type of vector in this entire course is the position vector. A vector that begins from the origin. Well, did I say we can choose any starting point? Because vectors do not depend upon the starting point. All these are the same vectors, you see. So we are free to take any starting point. So why don't I take the origin? That's the simplest starting point that you can think of. That kind of vector is called position vector because we have one-to-one correspondence between this position vector P and the end point, the tip of this arrow here. So if you have a point, x comma y, then you have position vector x comma y with round parentheses becoming pointed parentheses. Because of this relation, because of this one-to-one correspondence, there's no real fundamental reasons to distinguish one and the other, as a matter of fact. Does it make sense if we add 2 points, subtract points and things like that? In terms of point in geometry, that doesn't make much sense. In terms of vectors, oh yes, it makes perfect sense. It's a position vector. And we do those kind of things and just regard all the points as the tip of the position vector. We do those kind of things. Another important type of vector that we're going to consider to a certain degree in this chapter and probably never come back will be displacement vector. In physics this is important, but otherwise not very important. Certainly nothing compared with position vectors. Displacement vector has a starting point A and then ends at B. And how do we get that vector? Simply by subtracting. Subtract one from the other, subtract one from the other. Let me show you why. Yeah, okay. As a matter of fact, I prepared this graphics beforehand. Now, this picture and that picture are the same, except that this picture has auxiliary dotted lines, and that gives you a right triangle. And the horizontal component of this green vector goes from this x equal to -1 to x equal to 3. So what's the difference of x coordinate? From here all the way over there, 3 minus of -1, that's how I get 4. How about y components? Well, from blue to red, but if you look at only y component, then it's equivalent to just following this dotted line vertically here from the tip, from this corner of this right triangle to the red point. And what is it? -1 minus +1, that's how you get -2. And that justifies this formula here, x2 minus x1, comma y2 minus y1. That kind of vector is called displacement vector, important in physics, among others, but in math class, especially in this class, it's not as important, even half as important as the position vector. As a matter of fact, we're going to deal with other vectors to a certain degree here in this chapter, but once chapter 1 is passed, almost everything we do will be position vector. Now, we talked about some concepts of vectors. Let's talk about some formulas. Magnitude. Well, pretty simple, isn't it? And how to get a magnitude of a certain vector from 0, 0 to x comma y? Well, just distance from the origin to the tip of this arrow here using the distance formula, you're going to get that. And then this magnitude of the displacement vector, well, that's going to be nothing more than, I really wish I had that triangle back there. Yeah, this thing, okay. Using the triangle, Pythagorean triangle, you can use x2 minus x1 squared, horizontal, plus y2 minus y1 squared, vertical, and add them up and take square root. That'll give me the hypotenuse. That's how you get magnitude. Let's not squeeze too much information. Let's summarize. We talked about vectors, magnitude, direction, and algebraic rules. Algebraic rules include addition and scalar multiplication. And then every vector can be represented by components, x comma y, by regarding it as a position vector, which start from the origin. In some cases, we consider displacement vector, which start from some other point, but in this course, that's going to be rare. Finally, the magnitude, if you have just a vector, consider it as position vector, and you can use the distance formula from the origin to find out the magnitude of the vector. For displacement vector, you can use Pythagorean rule.